In this Mathematica tutorial, which is number 58, we're going to look at the tools of Mathematica programming. So there are a couple of things that you must know: how to operate functions, how to use logic in the computer, and one of the several loops that there are. But I recommend a while loop for a beginner because you often want to break out of the loop. Okay, so let's begin that. And if you're interested in that, stick with me for this one. So, functions, this is our first topic. So let's have a look at building a simple function first. So the first thing that we want to do is just build a simple function. Let's call it f. Now x will be our input, and we just put this underscore here and then a colon and an equals. And now this is a very simple example. Just the input is x, the output is x squared. Okay, so that's our first example there. Now another example is when we have two inputs, so an x and say the letter h, for example, or some other letter. So these are the two inputs of our function g in this case, and then the output involves both x and g, and in fact f, but f is in memory above it, and so this is the forward difference approximation of the first derivative. Okay, then we test it out. So g of 2 with a step size of 0.1. So that should give us an approximation of the first derivative of x squared at 2 with the step size of 0.1. Okay, and alternatively, this is how you do that if you're doing this by hand. This is the same forward difference calculation. It's just that the f squares, and so we have basically 2.1 squared minus 2 squared, and then we're dividing by 0.1 as our step size there. Okay, so let's go ahead and run this because that's already a fair bit there. So what we have is f has been put into memory, g in memory, and then the first output should be g of 2, which is approximation of f dash of 2. So in other words, 4.1. Now the next one is our alternative calculation of that, where we basically do it as we would do by hand. Okay, also 4.1. Now here's the analytic calculation of the derivative. So what I mean by that is just symbolically. So the first derivative of x squared is 2x, and so this is right here. Okay, and now the next thing that I need to show you is there's a way to sub in the x equals 2 into that symbolic expression. So I could use either replace all, which you see right here. So replace all 2x, x goes to 2. And this does the same thing. So in other words, slash and then the dot. And again, this does the same thing, because in this one we already know that the derivative is 2x, and then all we're doing is subbing in x is 2 there. So for each of these we get 4, so that's saying that the first derivative of x squared at 2 is equal to 4. Okay, great. So that's a simple kind of function, just colon equals. Now the next thing we'll want to do is learn about module. So module provides a way of putting certain variables in memory only inside the function. So they're not remembered outside the function. And I'll give you an example here. Okay, so I like to give my homemade functions a name, a person's name. Okay, so here I've got Steve, for example. So the function Steve, now notice it's lowercase here, whereas the built-in functions are uppercase in the beginning of the word. Okay, so it has two inputs, x and y. Now I'm using module, so I still have colon equals there, but module, and then in the first thing that I enter inside the module function, I put the letters that I'm going to have locally, remembered locally. So in other words, they should be forgotten outside of the use of the function. So what I want is a to be x plus y all squared and b to be x minus y all squared. And then the final result here is a plus b minus a times b. Okay, so that's what the function should do. Now, the reason to do this, in other words, use module rather than use what we have up here, just the colon equals, is because I'm calling on a and b multiple times, okay? So I don't want to have to calculate what a and b are multiple times, so this actually makes this more efficient for the computer to calculate. All right, so let's run this, and let's take the semicolon off of this one because this will be an example of exactly that. And we'll get minus 959 for what happens when we sub in 4 and 7. Okay, next, these are just other ways to do the same thing, right? So you can see this is quite lengthy here, but it's exactly the same thing. It's a plus b minus ab, exactly as we have there. All right, and then subbing in 4 and 7 for x and y respectively. Now this is exactly the same thing. We're using the slash dot instead of replace all in this case, and again, x goes to 4 and y goes to 7. All right, now next, notice how these are bright blue, the a and the b here, and they come out in the output 117 and 118, just as ab, and that's because they're not remembered outside the function, which is what we wanted to do here. Okay, so sometimes you want things to be remembered globally, and sometimes you only want them to be remembered locally. So that's the difference between the two types of, well, building of functions. Okay? Now, since this entire collection of problems comes from one of my students who didn't want to be on this video, this person had a number of questions, and so you might have the same questions. All right, so one of the questions was, in the help file, there was an example whereby in the brackets, the things that were put in temporarily here had an equals inside there, as in, so this is the same thing essentially, right? So we've got the same a and b, and then a plus b minus ab, but the difference here is that we don't just have a and b inside this these two curly brackets here. We also have what they're meant to be equal to locally. Okay, so you can also do that, and it works just the same. Okay, so let's move on. Now, also from the help file, I found a nice implementation of the Euclidean algorithm. All right, so let's go through this. Now, this is an example of a while loop in action. So it's possibly premature, but if you only get this far, then, well, this would be a nice thing for you to learn before you click off the video. Okay, so here we have a function that we're building, okay, so it's also using module. So it's really, let's consider it an example of using module. Okay, so this is lowercase, this is one that we are building. We have the colon equals, we have the function module there, and we're putting in memory m and n. And we're putting m and n in as m0 and n0 respectively. Okay, so now those m0 and, the m and the n are only going to be remembered inside this function GCD in lowercase. Now, what the function should do is run this while loop. Okay. So, and then once it runs the while loop, it will return the value of m, which in this case will be the GCD of the input numbers. Okay, and then we would just try this out. So let's run it. So the GCD of 21 and 15 is 3. All right, I thought I had another GCD. Oh, right. That's right. Here we go. GCD. Okay, so this one here is a built-in function, GCD, and it's probably just doing the same thing, running the Euclidean algorithm. Okay, now in this YouTube video here, which you can find in my list of videos, I'll go into further detail on the Euclidean algorithm and how it works. But if you didn't want to watch that, I'll just give you a simple example down below of a hand-calculated Euclidean algorithm. So basically, you have an m equal to qn plus r. All right, so the m and the n are the things that we're wanting to take the GCD between. But this is just expressed in terms of the quotient remainder theorem. Right, so the r is the remainder of m divided by n. Q is the quotient, so just the floor of m divided by n, so that it's an integer, and the remainder can be calculated with the mod function. Okay, so basically a simple hand calculation, so I don't want to go into too many details because I've already got a video on this uploaded. Okay, so if we were to take the GCD of 21 and 15 and do so by hand, we would say set it out by the quotient remainder theorem, and we've got to find the quotient and the remainder here. Okay, so 21 divide 15 and then take the floor, that gives us 1. So we put the 1 there where the Q1 was, and then we just can subtract, or we just take mod 21 comma 15, or 21 modulo 15. And that remainder is 6. So then what we do is we move the 15 over to the left-hand side of the equation, and the 6 over next to the quotient, and we've got to calculate a new quotient remainder. Okay, so we find that as 2 is the quotient, 3 is the remainder. Then we scoot those over, so the 6 goes on the left-hand side, and the remainder 3 goes next to the new quotient. And we repeat this. So in this case, we've got a quotient of 2 and a remainder of 0. So when we get to 0, we know that we're done, and so the remainder is just the 3. The GCD is the 3, and that tells you you're done with the algorithm. Okay, so what's happening up here is it's doing exactly that. Inside the while loop, which is running over it's iterating, say j equals 1, j equals 2, j equals 3, and so on. And you keep going until this test here fails. Right? So in other words, when n is not equal to 0, keep going, but when n is equal to 0, the test fails, and it exits the while loop, and we're done with running of that algorithm there. So what's happening here is m equals n in every iteration, so that's the shifting over of the number to the left-hand side of the equation, and then seeking a new quotient remainder. Okay, and then you set m as the remainder of m mod n. Okay, and then it outputs m. All right, so we should move on. Now, more about functions. So my student had a question about functions that remember the values that they have found. So again, this comes from the help file, but it's a rather interesting example. Okay, so the sequence here is just the Fibonacci numbers, right? So this is the recursive definition of the Fibonacci numbers there, and the first 2 Fibonacci numbers are 1. Now question mark f returns everything that it knows. So in this case, if we did it at this point, it would just return the values that it knows already, which is f0 and f1. However, if we then put f7, I think this is quite remarkable here. So you rather quickly get 21 as the, I guess if you want to call it the 7th Fibonacci number, not counting 0. Okay, so how does it do that? Well, it is basically putting in 7, and then it finds that, oh, I have to calculate F6 and F5 to get that, and so it's going down, 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 and in the process it's calculating several things. So let's take the comment off of this and let's just run that, because this will be interesting here. So it shows you everything that it's calculated to get that F7, right? So we got F7 is 21, and then all the previous ones that were required, and then here's the recursion there. Okay, so to build that, you just put the f of x right after the colon equals, and then the recursion after that. Okay, so all right, so I'll put a semicolon back on this to suppress that, and we'll move on to the next thing. So next, I've got another way to do that Fibonacci sequence. So in this case, I'm using subscripts, and this is the way that you might see it mathematically, or write it by hand. So, and I'm just using the table function here to do that, right? So I'm putting in F0 is 1, F1 is 1, and then here's the recursive definition, and then n goes from 1 to 7 in this case. So let's run this. See, this time we just get a list. So this is the numbers recursively calculated and produces this list. Okay, next thing, transformation rules for functions. So my student had a question about this one. Now this operator applies rules to all subparts of an expression. So in this case, it's going to replace the x with a 3. So this is like the replace all that we used previously, and we've already seen this used above. So let's run this. It'll run other things too, but I think I need to clear the f out of memory here. So I'll go evaluation, quit kernel, local. And then when I do that, I have to start the kernel up again. So 2 plus 2 will do the job. It'll take a little while. Because it's the first time. Okay, now we'll try this again. All right, so it should have done that now. Okay, so here is the output from this first one, where the x is being replaced by 3, so we have 1 plus f of 3 plus f of y. Now, the next one, the next example here, and I'll take the semicolon off of this, so let's run that too. Oh, hang on, this one. This is the one I want to run. Okay. Right, so what's happening here is we're saying everywhere when we have an f of something, the function is to square it. So everywhere replace that with the square of the input. So that would be x squared and y squared, and that's what we have in this output 9 down here below, 1 plus x squared plus y squared. Okay, and now it's important to note that when we're using this procedure, we haven't put it in memory. We haven't put f, the function, in memory, so the fact that f of t is t squared is not remembered outside of that line there. So f of x is just returning f of x there. Okay, moving on. And incidentally, if you've got questions or comments, please put those in the comments below. I'll have a look at them and maybe even answer them. Okay, so more transformation rules examples. So this one here, it's a little bit tricky. So let's run this. Okay, so what's happened here is we've got f of AB plus f of CD, and this is saying wherever you have f of a product, replace that with f of the sum. Okay, so then that would say that f of AB is f of A plus f of B, so that's what we have here, and likewise for this one. Okay, so great. Now, that's good because you can use this to do things like program into Mathematica some logarithm rules or log rules, or other kinds of mathematical rules that you might use, right? And I'll give you an example in a moment. So this one here says when you have an integer power of x, then replace that with f of p. So let's run that. Okay, so we have 1 plus f of 2 plus f of 4. Those are the powers there. So that's handy to be able to do that. All right. So, like I said earlier, this is a way to... Hang on, is this correct? Yeah, this is a way to use replacement rules like real-life log rules and so on. Now, I'm seeing this double... I think that's wrong, so let's run this and see. Or maybe it's not. It seems to work. Okay, what happens if I take it off? Sure, so I'll have to think about that one. But let's have a look at this, sine double. So I've put this in sine double. So what I mean is to put the double angle formula in use. So sine of 2x is equal to 2 sine of x times cos of x. And so the question here is, what is sine of 2 times 1 plus x all squared? All right, so we've got slash dot sine double, so we're going to use this replacement rule here. And let's have a look. Okay, so it gives us 2 times the cosine of x plus 1 squared times sine of x plus 1 squared, which is correct. Okay, next, the map function. So the map function is applying f to each of the elements in the second argument of the function. Right, so there are two ways to do this. You could have a slash at, or you could just write map. So let's have a look at this, run that. So you see it's applied f to every element of this list. Also sometimes very convenient to be able to do when you're programming in Mathematica. Okay, then we'll come to the notion of pure functions in Mathematica. So this one's possibly a little bit more tricky, or takes some getting used to. So let's have a look at what it does here. So we have this hash sign that we put inside the function, and then we use this and. Okay, now we're using map at. So basically it's saying apply this, the map at part is saying apply this to every one of those entries here one by one. So in other words, 1 plus g of a, comma 1 plus g of b, and so on. So just as we have here. All right. Now some alternative ways to do this. Here I'm building a simple function here that just adds 1. So it takes the argument q, adds, it's 1 plus g of q there. Okay, but I haven't said what g is as a function. And then I'm using the map function here, the slash at. So it applies it to each one of those. Now, the final alternative way to do this here is just to use the table function. I tend to use this one a lot because it's just pretty straightforward. But as I do that, I have to index on this array here. So I say S equals A, B, C, D, E, and then the input of G here has to be the jth element of S. Okay, and then I'm tabulating as J goes from 1 to 5. Okay, so 3 different ways to do that. All right, then we have this one here is quite tricky. So we've got hash squared and then we're applying it to this expression. So basically it takes each of these and squares them and retains this plus sign. All right, so I would say use this one with some care here. You want to practice looking at how this works before you're ready to go using that. All right, so double hash here means all arguments. So let's have a look at this. So what we have here is we're applying each of the x and y there and there as well. Okay, next we are going to look at some logic, because logic is an important ingredient in building some Mathematica code, or any kind of code for that matter, right? You want to know what are the logical symbols and how do I put them together. So I'm going to keep this section short and very simple. So you first need to know negation. So in Mathematica, that's putting an exclamation before a proposition. And in this case, let's just have a look at true and false. So it should turn the value of true into false and the value of false into true. So let's run that. Okay, so we get false and true, so they're the opposite truth values there. Now equivalently, you could use the function not. So not true gives false, and not false is true. Okay, so two different ways of doing the same thing. Next we have and. So for example, true and true is true, but true and false is false, and so on, right? So it means and just as you expect, and it's two and signs on the keyboard next to one another. All right, the next one is or, and so let's do something similar for this. So true or false is true, so we have true and true as our outputs of this, and that's just two vertical lines. So on my keyboard, that's shift and then above the enter. So just verify that. Okay, it comes out pink, and then I make another one. It's still pink, but if I put something in front, so false, we have or and then false. Okay, now it's turned black, so it's good to go. So that should be false. All right, great. Okay, and then the last logical thing that you need to know in terms of programming is if then, or implies. All right, so here I've got a false statement, so 3 is the smaller one, and so I said if this holds true, then put yep, and if otherwise, as in if it's not true, then put nope. Now these are strings, right? So that's to the left of the enter sign, the quotation marks, so that will produce a string. Okay, and now in this case here, the condition or the test is true, so I should get yep. I should get nope and yep. All right, great, as expected. All right, so now putting it all together, right? So to put it all together and build your own programs, you want to know at least one of for, do, while, etc., right? But I'm going to just focus on while here. Because I think it's useful, and it's a reasonable thing to start with. Okay, so the basic structure here. Now this is one my student brought up, pointed out of the help file, and he had a few questions about what's going on here. All right, so again, we're using module. We're building our own function here. We're saying that inside the function, x is to be remembered as the input of the function x0. And then the body of this, what we're going to do in the function is we're going to run this while loop, where the output of the function is the x that comes out of the while loop. Okay, so what this while loop is doing is it's saying that while x is greater than 0, in each iteration set x as log of the previous term or iteration, right? So in other words, what you're doing is you're nesting log on itself. So log of log of log of log of log dot dot dot. Inside this is the first one, which would be the input of that function. Okay, so let's run this and then try it with the number 2. Okay, so the output of the function here is minus 0.366 and so on, right? So it has broken out of this when this test failed, because you see suddenly you get a negative number, so the test fails, and so it exits the while loop and just returns x there as written, and that's the output of that function. Okay, so the question now is, can we do this in another way? Now, I don't know what my student's question was here, or why I have table j squared there, but right here I just have a very simple example of that while loop. So let's run this. All right, so we get out just the one number, and it's the same number here as in the function. But also several things might be calculated in this, right? So let's just change this a little bit so I can illustrate. So if instead I put a semicolon there and then I write print x inside this while loop, okay, now it's showing what happened in each iteration. Right, so in the first iteration you would be taking log of 2, and then in the next iteration, because that turns out to be positive, you keep going in this function, or in the while loop, and so you take log of 2. All right, so let's run this, and you see what we get. We get 0.69314, etc., and then log of 2 is minus 0.366513. Okay, so that shows what's going on in this while loop here. All right, and then that also shows what's going on in this module function here, because the body of this module function here is running that while loop and returning the last x, the x that you got when it broke the while loop. Okay, but it's applying this as a function with a local variable there. Okay, great. Let's keep going. Now here are some simpler examples of a while loop in action. So this looks like the same one, which I've already shown you. Okay, now what's this one? This is an even simpler one. In this case, what I'm doing is I'm just updating, saying add 1 to x in each iteration and stop when this test fails. So in other words, when x is equal to 11, because we're starting with an integer here, and print out the x's in each case. So let's go ahead and run this. Okay, so you can see what we get. We get 2, 3, 4, up to 11. So the x's that we're printing, so the first x we can print is 1 plus 1, which is 2. And then we print out the last one when we broke the while loop there. Okay, good. Let's have a look at our next example. Now, if you look in the help file, you see examples in which you have a plus plus. And now this looks a little bit like C++, but it's not. I think some order is reversed, if I remember right. Okay, so we could, here's our test, and then what we're doing is we're saying print x, all right? X is starting out as 1, but I think we actually don't need that, I'm not sure. But here we're saying add 1 to it in every iteration, so update. And this will just run the same thing, except we start with a 1 there. Okay, next one. So this is a little bit of a precursor to the question that my student had about something that he found in the help file. So the first, it's down here, right? But it's got some things that perhaps he didn't quite understand immediately. So this one I've got prompt the user to enter some info. Okay, so if I run this input, and then I've got this string here. So this is going to give me a question in a little window, so I'll run that. And you see here the window comes up, and I'll just say Sam, and then I'll press OK, and then it just returns what I entered there in the window. Okay, and I could set this, I could put this in memory too. For example, W equals this, and then I'll run this. Okay, and then I'll write my name. Okay, and then it's done, and let's go into a new cell now and just see if it remembered that. What is the value of W? It's Sam, all right? So there we go, and that's not a string, this is just as a variable. Okay, so that's one ingredient in this. And now we've also got some logic being used here. So this is where we put things all together. So this one says while. Now here's the test. The test is it true? So you set n equals input, enter an integer, right? So this will prompt the user to enter an integer in the window. They press OK, and then it proceeds to calculate. Okay, so once that part is done, next you are saying if it's not an integer or n is less than or equal to 0, then break. Okay, so basically if you disobey the rules, and so this should really say enter a positive integer. All right, and so there's our little test of when we should break. All right, and then what we're going to do is print the integer that the user put in, and then a string that says equals, and then put in the factorized form of that integer. Okay, so if the user obeys the question here, then they'll get the factorized form. So let's try this. We'll just run that there. Okay, so we now have to enter an integer. So let's enter a simple one like 15. We know this is composite. Okay, I don't know why it's now suddenly saying enter a positive integer. But what we've got here is the factorization, the canonical factorization of 15. So 3 to the power of 1 times 5 to the power of 1. Now I'll just put it in again and see what happens. Okay, it's going to ask me this again. Now what happens if I put in a negative number? So minus 36. Okay, and then it's just broken. It hasn't given me anything, so that's what's going on here. All right, so it's just terminated that. Okay, so next let's talk about putting together a very simple routine. So this one will be Newton's method for approximating the square root of 39. Okay, so I might have talked about this in another video. So I also have a video on Newton's method, so you can go check that out. I've got some nice geometric images to go with it to explain some aspects of it. But let's just talk about the programming of this. So we've got f of x is x squared minus 39. So this is the function whose roots we need to find. Okay, and then this is the next term in the sequence that Newton's method would have you calculate. But in the denominator here, I have the first derivative of f of x, which I just have in symbolically. That's fine, because this is fairly simple as a function here. Okay, now you want to test the functions once you do this sort of thing so that you can debug early. All right, so let's go ahead and do that. So f of 1 and g of 1, see what we get. Yes, we expected to just get whole numbers. All right, so if I put a decimal place in these, I should get decimal numbers. Great, that works. Now let's go ahead and take the actual square root of 39 numerically to 25 decimal places. So here is the function square root of 39.0, but I'm saying take that numerically up to 25 decimal places, and I don't need the 0.0 there. Let's go ahead and have a look. Okay, so there we've got 25 decimal places of the square root of 39 so that we can compare our results here. Okay, so in this one, what I want to do is calculate or set out a tolerance, right? So I say TOL equals, and now it's just, what is this, 5 decimal places there, a 1 in the last place. And then the next one says x is equal to the numerical value of 2 to 25 decimal places, y equals 3, and then I have a while loop. So what I'm saying is, while the absolute value of y minus x is greater than the tolerance, then continue. Okay, but I'm going to set this out as y being the one after x, and then I just update that. So this is a sequence I'm running here. Okay, so first we've got x is equal to y, because we're running, each time you update, and then y is equal to g of x, so this just runs this sequence, so y is the next term in the sequence, and then I want to print x comma y. Okay, so let's go ahead and run this. And you can see here we have fractions, which is not quite what you want. Okay, so in this case, but you can see that it's been terminated because it's measuring this against the tolerance anyway. So if we go and put in a decimal place here, that should fix this up, or at least I thought it would. Maybe they both need to be that way. Okay, now that's fine. And so now we get the numerical approximation of that square root of 39. Okay, so let's just copy one of these, the last one, and paste it there. And so we can compare this against this one calculated by Mathematica's built-in function up to 25 decimal places. So we have 6.244, okay, so those agree, 99, and then they're different here. Now that's different in the 6th decimal place, but that is because the tolerance is set in the 6th decimal place, right? So if I extend this tolerance, then I should get more terms. Well, let's have a look. Okay, so I keep going. So there's more and more accuracy in these. So I'll copy this and paste it underneath. And so now we see the 799 there, 83, and so on. Okay? All right, well, that's all I have for you. I hope to make more videos like this in the future, so please subscribe, and I'll see you later.